Welcome back to another math lesson here, an Algebra 2 lesson. We are starting a new unit today, Unit 3, which is quadratic methods. We're going to work on some techniques that we're going to use as we start to look at quadratic functions. So some of these will be review techniques, some of these will be new techniques. Today we are focusing on QM1 notes, complex numbers. And specifically in the portion of complex numbers, today we're going to focus on imaginary numbers. So imaginary numbers may be a completely new term for you. We've been primarily working with real numbers, only working with real numbers this entire year. Maybe most of the time in your math career, you've been working with only real numbers. Now we're going to find a new set or new distinction of numbers that we can work with called imaginary and complex numbers. To do so, let's go ahead and take a look at problem number 1 and problem 2 in your notes. So if you have yet to complete problem number 1 and problem number 2, pause the video and do that first. If you have completed it, now let's follow along and let's take a look at answers. So under the discovery for complex numbers and complex solutions, which is going to lead us beginning with imaginary numbers, it says recall from Algebra 1 that a zero for a function is the same as a solution for a function. So a zero means solution. In other words, finding a zero for a function f of x equals ax plus b is the same as solving the equation where we set ax plus b equals to 0. These zeros can be found algebraically and graphically. So graphically, the zeros or solutions are the locations where the graph of a function intersects the x-axis, or as we talked about in the last target, the x-intercepts. So in problem number 1, it says consider the function f of x equals 1/2 x plus 3. Use algebra to determine any zeros or solutions for the equation. So in order to do that, we need to set the function equal to 0 or replace f of x with 0. So now we have 0 equals 1/2 x plus 3. And we can solve this equation for x in order to find the solution, or the 0, or the x-intercepts. So first, I'm going to subtract 3 from both sides, and then multiply the function by 2 in order to eliminate the 1/2. So I have -6 equals x. So x is equal to -6, and that is my solution, or my 0, or should be my x-intercept for the function. So in order to complete the same problem graphically, we can graph this line. We should know how to graph this line. We have the y-intercept, so we're going to plot the y-intercept at +3. We know the slope is 1/2, so we could plot points by counting up 1 on the y-axis and +2 to the right 2 on the x-axis. We could also do the opposite of that, so we could count down 1 on y-axis. So I'm going to go back to my y-intercept, count down 1 on the y-axis, and left 2 on the x-axis. And I can continue to do that until I plot enough points to graph the line. 2 points would be sufficient, but if I go a little bit past 2, that's okay. And now I have a path to graph my line here. And here's the graph of my linear function. And I can verify the solution here as the x-intercept by taking a look where it intersects the x-axis. And it would be at this point -6, 0. So the x-intercept, -6, is the same as the solution, -6. Now, let's go a little bit further. If we take a look at problem number 2, it says, consider the functions h of x equals x squared minus 1, and g of x equals x squared plus 2. Graph each function separately in the coordinate planes below. So these are both quadratic functions, which you did learn a little bit about in Algebra 1. We haven't done a whole lot in Algebra 2 with them yet, so we're going to go ahead and use the graphing calculator to graph those functions. Get that graphing calculator up and expand this window. So you could graph these by hand if you remember from Algebra 1, but let's graph these using the calculator. So I'm going to type in the function as I read it, x squared minus 1, And I'm going to go under the standard window for my graph, and there I can see the parabola. I can also take a look at the table to look at points that exist on this curve. So either graphing using the parabola or the window frame that it gave us, or graphing using the table, I can plot some points and graph my curve. So I'm going to plot the point 0, -1, 1, 0, -1, 0. I'm going to have the point 2, 3, and -2, 3. I'm going to have the point 3, 8, and -3, 8. And all other points will end up off my graph. So here is the graph, rough sketch, but here is the graph for h of x. G of x would be similar, but it's going to be x squared plus 1. So I'm going to take a look at the graph here first. It's another parabola, but it's shifted up. We should know the difference between these. We have a vertical translation down 1 and then a vertical translation up 1. So this is shifted up 2 units from the previous parabola. And if I take a look at the table, I can again use the table to help me plot some points. So I would have -310. I'm also going to have +310. I'm going to have -2, 5. Also +2, 5. I'm going to have -1, 2. Also +1, 2. And then I'm going to have 0, 1. And I can sketch in this parabola. And there we have g of x and h of x on our two coordinate planes. Now it says by viewing the graphs, list the zeros for h of x. So remember, zeros are the x-intercepts. So I have an x-intercept 1, 0, and -1, 0. So the zeros would be those x values. So x equals -1 and x equals +1 would be the two zeros for h of x. We can see that there on the graph where it intersects the x-axis. Now, if I take a look at g of x, it says, viewing the graphs, can you list the zeros for g of x? You should have said, no, you cannot. And because g of x does not have any intersections with the x-axis or does not have any x-intercepts. Now, this does not mean that g of x does not have solutions. This is where imaginary units come into play. So what an xy coordinate plane does is it shows us every real number solution that exists for a function. But there are potentially other solutions that can exist for functions. G of x does have two solutions, but its solutions are found using imaginary units. So an imaginary unit, basically what we do here to give you a semi-pseudo definition here. We use this variable I to represent an imaginary unit. And we use this value in expressions. This is where I squared is equal to -1. So an imaginary unit I is explained because I squared equals -1. Now what this leads us to is that I is the square root of -1. So if I wanted to get I by itself, I'd square root both sides, right? And then the square and the square root would cancel out. And so I would equal the square root of -1. And so this is where in Algebra 1, you probably came into some problems. Because in Algebra 1, when you talked about square roots, you probably said you cannot square root a negative number. And let's go ahead and take a look at number 3. It says, rewrite each of the imaginary numbers in terms of I and simplify if possible. So if I try to type in my calculator the square root of -7, it's going to come up with what it says error, non-real answer. meaning that I can't simplify this expression using real numbers. But when I have a negative square root, now, based on what we just learned with imaginary units, we can simplify this expression. The way that we would simplify this expression is by essentially breaking apart the square root into the square root of -1 times the square root of 7. And the square root of -1 is just I. So this would be I times the square root of 7, or often people write this as the square root of 7I. Either or would be okay. I generally write it as I square root of 7. So this can be simplified. The square root of 7 cannot be simplified, but the expression can be simplified by getting rid of the negative number inside the square root by using the imaginary unit. Let's take a look at B. In B, I had the square root of -81. So again, I can break this apart into the square root of -1, or actually, I'll go ahead and write the whole number first. Let's do the square root of +81 times the square root of -1. So remember, square roots can be broken apart so that their inside values, the radicands, can multiply to one another. So the square root of -81 can be broken apart into the square root of 81 times the square root of -1. The square root of 81, we know, simplifies to 9. Now, it does not need to be plus or minus 9 because we are simplifying and not solving. We'll get to more detail on that later, but for right now, it's just 9. The square root of -1, if I simplify the square root of -1, is I. And so this expression simplifies down to 9I. In C, we can do the same thing. However, in C, we're going to find a different simplifying process. So the square root of 24 times the square root of -1 is how we can break down this expression. Now, the square root of 24 is not a perfect square. I cannot take the square root of 24. So if I tried to do that in my calculator, I would take the square root of 24. Oh, sorry. The square root of 24 here, and I'd come up with a decimal answer, which is not going to, we're going to give our exact answers. We're not going to round here. So what I'm going to do instead is I'm going to break the square root of 24 down into something that I can take the square root of. I'm going to break it down into 4, or the square root of 4, times the square root of 6. And then I'm still going to have times the square root of -1 down there in the end. Why did I choose the square root of 4 times the square root of 6? Well, 4 times 6 is 24, so I didn't change anything. I just broke these apart. But now I can take the square root of 4. What's the square root of 4? If you said 2, you'd be correct. And I can also simplify the square root of root -1, which is I. And now I have the square root of 6. Now I could potentially break down the square root of 6 into square root 2 times square root 3, but I can't take the square root of either of those numbers. So the square root of 6 is as low as we can go here. So 2I square root 6 would be our simplified version here. Sometimes people also write this as 2 square root 6I. That's okay as well. So the imaginary unit is allowing us to get rid of the negative value inside of square root, not get rid of it, but replace it with a variable, and then we can simplify our equation. Let's try one more. In D, I have a -3 out in front of the expression. I'm going to leave that alone. Then I'm going to take -16, the square root of -16, and break that into the square root of +16 times the square root of -1. Now, what's the square root of +16? If you said 4, that would be correct. So now this becomes -3 times 4 times the square root of -1, which is I. And we can simplify a little further. -3 times 4 is -12. And so this expression becomes -12I. So what imaginary units allow us to do is it allow us to come to simplify roots, square roots, or fourth roots that have, sorry, just square roots. So square roots that have a negative number inside in the radicand. Now, powers of I are very important. So in problem number 4, it says simplify each of the powers of I. We already said what I squared was. I squared is -1. I is the root of -1. I squared is -1. Well, then what would I cubed be? Well, I cubed is the same as I times I times I, which is the same as I squared times I, which would be -1 times the root -1. Or we could just simplify this as -1 times I, or just -I. I to the fourth power. I to the fourth power can be broken down. It could be broken down into 4 i's, or I'm going to go ahead and break it down into I cubed times I. Why I cubed times I? Well, we know what I cubed is. I cubed is -I times I. So -I times I would be -I squared. Well, what's I squared? Let's go back over here. I squared is -1, so this is basically -1, which would make this +1. So I to the fourth is +1. Let's look at I to the fifth. I to the fifth is the same as I to the fourth times another I. I to the fourth we know is +1. So +1 times I is just I. We should start to see a pattern develop here. I to the sixth. I to the sixth is I to the fifth times I. I to the fifth we know is I. And so basically this is I times I, which is I squared, which we know from part A is just -1. Now on to I to the seventh. I to the seventh is just I to the sixth times I. I to the sixth is -1. We just found that out. So -1 times I is -I. We can continue this pattern. You may see the pattern starting to arise already. I to the eighth is the same as I to the seventh times I. I to the seventh, we just found out, was -I. So this would be -I times I, which is -I squared. And I squared is -1. So this is a -1, which is a +1. Now, if you see the pattern, what do you think I to the ninth is? Hopefully you said it's just going to be I. Well, let's check. I to the ninth is I to the eighth times I. I to the eighth is 1. So 1 times I to the ninth is I. So we may see this a pattern start to emerge here. So I to the first power is just I, which is the square root of -1. I to the second power is -1. I to the third is -I. Then +1. Then +I. Then -1. -I. +1. +I. So notice that there's kind of an emerging pattern here. We go with I, -1. -I, +1. +I, -1. -I, +1. +I, -1. And so on and so forth as we continue this pattern forever with powers of I. So what we may notice here is that this continues to repeat based on the 4 first powers of I. So I to the first power is just I. I to the second power is -1. I to the third power is -I. And I to the fourth power is 1, +1. And then these will continue to repeat and repeat and repeat as we increase powers of I. And so that's going to allow us to solve a problem like we see in problem number 5, where we have very high powers of I. And we will take a look at that in class when we reconvene. So this is a good place to stop with imaginary units. Tomorrow in class, we will look at this problem and then give you some time to practice with powers of I. Thank you guys for tuning in. I'll see you soon.